Hello, this video is entitled Space Coordinates and Vectors in Space. So now we're stepping into the world of multivariable calculus, where we are no longer just in the XY plane. We now have a third dimension. Let's take a look at so in addition to our normal X and Y axis, we have a Z axis. Now this is, I pretty much stick with what's called the right-handed system. There's one called right-handed system, there's another one called left-handed system. So if you are in a situation where, you can look into that. All that essentially is if you reverse the X and the Y axis. That's called the left-handed system. And Z is still vertical. Now, XY coordinate system, we just have the XY plane. But now with these three different axes, we have three different planes. So you see your base plane here with X and Y, that's still your XY plane. Now, this direction is your XZ plane with the X and the Z axis. And then with the Y and the Z drawn like this is your YZ plane. Then they're telling you that X is your distance from the YZ plane to whatever your point P is, either this direction, which is positive, or that direction, which is negative. And it's the distance away from that YZ plane. Y would be the distance this way. And it's the distance away from the XZ plane, with this side being positive and this side being negative. And Z is the distance from the XY plane to your point P, up for positive, down for negative. Now, I don't think you have to be highly skilled in plotting these points, at least not in my class, but just kind of understanding how they work is a good idea. It's a little tricky trying to, draw three-dimensional things in a two-dimensional surface. But let's just kind of take a look at some of these. So these are, now we call these ordered triples instead of ordered pairs. They always go X, Y, Z. So let's just look at these points and you can see how these are drawn real quick here. So the point 2, -5, 3 would be represented as 2 units in the X direction, 5 units, positive X direction, 5 units in the negative X direction. You see how the axis is labeled there. And then they draw this line and that line to make it all nice and neat. And then the tough part here is, drawing the vertical part, just trying to estimate. But anyway, that dot does represent, this height of 3 right here. Well, it's a little tricky, but I think it's not hard for people to pick up here. And here's 1, 1, 6, 0. So 1 positive, 6 in the positive Y direction, and 0 means you're not going up or down. So one thing to kind of keep in mind that may just come in handy, I don't think it's that critical that you memorize it or anything, but anytime that your point is on the XY plane, and we might come up with situations where we, that would come in handy to know later, so maybe we should take a look at this. But if you're in the XY plane, that means your Z coordinate is going to be in the 0. If you're on the XZ plane, your Y is 0 because that's the distance right here, because that's the distance from the XZ plane. And if you're in the YZ plane, your X coordinate would be 0. So, for example, if a question asks, would the point 0, 6, 4 be on the YZ plane? And the answer is yes, because the X being 0. Wouldn't matter what the other two were. They would definitely be in the XZ plane, YZ plane, excuse me. As you can see, 1, 6, 0, because the Z being 0 means that point was in the XY plane. So we have kind of 8 sections on this graph now instead of, we had 4 quadrants. These are called octants. You have 4 of them above the XY plane and 4 of them below. Now, I haven't worked with much The only one that I really worked at with as far as being numbered octant, in fact, I'm not sure. There might be a system out there that numbers the octants, but I've never needed to know. But when we say first octant, that's the one where X, Y, and Z is positive. And that'll come up, later. We'll say blah, 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 first octant. That's all we have to know. But I've never asked any questions that involve any octants because you won't even see me define them in here anywhere. And none of the problems in this book or the assignments will have any numbered octants. But it is possible that maybe some textbooks do bring that up. Alrighty, a lot of things you're going to see here with these equations are the same as they would be for two variables, but you're just adding z in there. So the distance between 2 points in space, using the distance formula, and so in other words, if you cut it off right here before the blue line, that's just your basic distance formula in algebra. But then now the difference in space is we just add the difference of the z squared. So now it's the difference of the x squared plus the difference of y squared plus the difference of the z squared. Now, 2 dimensions, we have something called a circle that has a center and a radius, but obviously that's a 2-dimensional shape, a circle is. But in 3 dimensions, we have what's called a sphere. And we can come up with an equation of a sphere pretty easily. And it looks just like the circle equation, except it has a z in there. So it's x minus x0 squared plus y minus y0 squared plus z minus z0 squared equals r squared. R is the radius, of course. And the center is x0, y0, z0. Midpoint between any 2 points. If you take any 2 points, and connect a straight line between those 2 points, well, midpoint, once again, it just adds a z to it, like a regular midpoint formula in algebra. Just toss a z in there, and there you go. So it figures out the halfway point on a straight line. One thing that I can think where that would be used is if you have a problem. Sometimes it will give you information involving points on a circle, and it'll say that, okay, you got sphere. And well, it could be done for circles in 2 dimensions. But sphere, let's say you have 2 points on the edge of the sphere and that run a straight line through the center of the sphere. Well, then the center of the sphere would be the midpoint of those 2 given points. So that's how you would figure out what the center was, is using this formula. So just in case that comes up anywhere. Now we're going to find the equation of the sphere in its standard form. Now notice how this number, problem 41, notice how the information is given to you. It's given to you in an expanded out form there. So we're going to have to do some algebra there, completing the square to be able to get our form that we need, the standard form for the sphere. So notice I kind of grouped the x's together, I grouped the y's together, I grouped the z's together. I moved the 1 over to the other side to make it -1. So to complete the square, you take half the middle term, -2, which is -1, square it, that makes 1. This one you take half of 6, which is 3, square it, that makes 9. Take half of 8, which is 4, that makes 16. So we add 1 plus 9 plus 16. So whatever we add to the left side, we must also add to the right side, which I've done there in red. And that enables us then to create these perfect squares right here. So we have x minus 1 squared, and then we have y plus 3 squared, z plus 4 squared equals 25. Now be careful, because look at the way the formula, just like with circles in algebra, you have to be careful how you determine what the center is, because the formula, is x, they're all minuses. So it's going to be the opposite signs. So that's going to be +1, not -1. And this would be -3 because y minus -3 makes +3. And then that 4 is going to be a -4 because the formula is subtraction. So be careful with that, not to get that messed up. And the radius is easy. The radius is just the square root of whatever's on the right side. Doesn't have to be a perfect integer. In this case, it just happens to be. I mean, that could have been 21, and we could have had the square root of 21 as a radius, no problem. So that sphere is going to have center 1, -3, -4 with radius 5. And I use the Maple software. Do not worry, you're not ever going to have to do anything like this in my class. But I thought it was kind of neat looking. So it's there it is, 1, -3, -4 with radius 5. So it kind of, you're going 1 unit out in the positive x direction, and then 3 units to the left. All right, let me change this over. So it's 1 this direction, 3 to the left, and 4 down to find the center of that sphere. So somewhere in there. And then 5 out to the edge from there. All right. But that's not important, but I thought it was kind of neat to take a look at what it looks like. Vectors in space. Let's take a look at this. And in another video, I've talked about standard unit vectors I and j. Now we have standard unit vectors I, j, and k. So here's the component form for a vector v, where it's, remember, we use the angled bracket again. Not parentheses only represents points. Angled brackets are vectors. v1, v2, v3, the z component. The 0 vector is 0, 0, 0. And then now the ijk, well, now we have a new one, k, but even I and j add an extra 0 there. So I is 1, 0, 0. One direction, 1 unit in the x direction. J is 0, 1, 0, 1 unit in the y direction. And then k would be 0, 0, 1, 1 unit vector going upwards. So component form and standard unit vector form can be used interchangeably. So this standard unit vector, you would have v1i, v2j, v3k, and then component, you put it in the brackets, angled bracket. Yeah, you'll see a lot of problems that I do and stuff. If they give the original information in standard unit vector form, I'll quite often just convert it to component form. I think it's a little easier to write without having to write the I, J, and K. I just prefer the standard unit, the component form a little bit better. So look at this one, -3i plus 6j minus 7k. How would we write that in component form? It would be -3, 6, -7. 7i minus 5k, got to be careful. There's no j there, so we have to realize that. So it's not just 7, -5. We have to have a 0 in there. Now, of course, we have to, if it just gave I and j, though, you would have to know that it would somehow have the information to know that it was a space vector, because I and j could just be a vector in the plane, but then that just means you would add the 0 at the end. But obviously, this one is a space vector without even telling you, because it has the k in it. So that gives it away automatically. But I and j could be a little tricky, because there'd have to be enough information to whether you should know it's a plane or a space. A lot of stuff's pretty much the same as it was in 2 space for 3 space. A lot of this stuff is. Here's u and here's v. Okay, so u equals v if you have the same components. Look at see that you want to come up with a vector between 2 points, vector p to q. You know, just like we did with 2 of them. So now we just have a q3 minus p3. That's the only difference. So we already had q1 minus p1 before, q2 minus p2. Now we just have a q3 minus p3. Length or magnitude, you just add another component there. So before it was just v1 squared plus v2 squared. Now it's plus v3 squared, all under a square root. Unit vector, exact same formula. It's just a third component there now. So it's 1 over the magnitude of the vector times the vector itself. Scalar multiple. That's 1 over magnitude of the scalar times that vector. And okay, all the stuff's pretty much the same. All right, this one's easy. Can we find the vector between the initial point and the terminal point? So it's always terminal minus initial. So 2 minus 1 makes 1. 4 minus a minus 2 is 6. Negative 2 minus 4 is negative 6. And then what's the magnitude also? And then a unit vector in the direction of the vector v. So this is just like plane vectors. If you wanted the opposite direction, you would just change the signs of each of the components. But here, we calculate the magnitude, which is 1 squared plus 6 squared plus negative 6 squared, which will give you root 73. So it's your vector v, then just each term divided by root 73. That gives you a unit vector going in the same direction. Now let's talk about parallel vectors. This also applies to both plane and space. So there are some things here that they're defining that they could have defined in the last section, but they've waited until to do it both at once. So this covers both plane and space. Two vectors, u and v, are parallel if there's some scalar c where u equals c times v. Now don't confuse parallel vectors with parallel lines from algebra. Remember, vectors can move around. You can, as long as they have the components, you can start them from anywhere and finish anywhere. Parallel lines would not actually touch each other. But, you could take this vector v and put it right on top of that vector u, and they're still parallel is what I'm getting at. In other words, that doesn't affect whether they're parallel or not, because they can kind of move around. The only thing is it just has to be one has to be a scalar multiple of the other. Of course, if they're the same vector, they're obviously parallel. Like this one's telling you that vector u equals 2 times vector v. So wherever I put vector u and vector v, wherever I start and finish them, that would not change the fact that u equals 2 times v. Therefore, they are parallel. And here they're telling you w is equal to negative v. So that just means it's going the opposite direction. So opposite direction vectors are still parallel. So technically, all three of these vectors are parallel to each other. Yeah, so the direction makes no difference. It just means the scalar multiple right here, where the c is right there, would just be negative. That's the only difference. It just changes the direction. So you got two vectors, and you want to know whether or not they're parallel. I guess I should have maybe put some instructions in there that say determine if these vectors are parallel, but okay. Maybe I'll add that in there after I finish this video. Well, there's two ways you can do it, because one of them has to be a multiple of the other. So I'll start with v. But if you just take v, each component of v, and divide it by each component of u, if they all divide to be the same scalar, then they're parallel. If any one of them is different, then it's not. In other words, negative 6 divided by 2 is negative 3. 9 divided by negative 3 is negative 3. And then negative 12 divided by 4 is negative 3. So that guarantees that vector v is negative 3 times vector u. Therefore, u and v are parallel. Or the other way, you could say u is negative 1/3 of v, same thing. They are parallel. But you can just check them component by component by dividing. And if they all have the same ratio, then it's parallel. Okay, I decided instead of waiting until after the video to go ahead and go do that, pause the video for a minute and actually put the question in here, are vectors u and v parallel? So now there's actually instructions with the problem. All right, this one has instructions. Okay, this one's kind of interesting. They give us 4 points that form the vertices of a shape, and this one, they're guaranteeing it's a parallelogram, but obviously a question could be asked, do the points form a parallelogram? Obviously it could be just, a random 4-sided surface there, but I guess they're kind of giving it away right here. So they're given these 4 points. Now, Got it? Now, do we? You might be wondering, geez, do I have to graph these or plot these in space or anything like that? No. So if you randomly come up with between these 4 points, you can get 6 vectors, pairing each one of them up, and you get 6 vectors. And then this what I'm trying to show you in this diagram over here, I'm just using arbitrary letters A, B, C, and D. But if it's going to be a parallelogram, what's going to happen is you're going to have 2 sets of parallel vectors, and that'll guarantee it's a parallelogram. Now you get this one. In this case, the way I've labeled it, AC and BD would be parallel, and then AB and CD would be parallel. The other 2 are just going to be the diagonals. So when you compute these vectors, you don't really know what you're, when I look at it, I don't know which one's going to be, so 2 of them are going to be like meaningless diagonals. But what we're looking for is 2 pairs of parallel vectors. Then we know we have a parallelogram. So let's see what's happening here. So once again, to calculate the vectors, that's easy. I won't go through every one of these, but for AB, I'll take the first one. 9 minus 1, that makes 8. Negative 1 minus 1 makes negative 2. Negative 2 minus 3 makes negative 5. And see, notice these are parentheses because they're all points. But notice that when I make vectors out of them, they're now in component angled bracket form. So you don't want to get parentheses and vector component form confused. So I calculated all, by just labeling them A, B, C, and D, I calculated all possible 6 vectors. And then I look at this, and I look at A, B, and C, D. Now notice they're the same numbers, but they have opposite signs. That's okay. That just means one of them's a -1 multiple of the other. And by the parallel definition we learned earlier, that's good enough. I didn't say they had to run the same direction. They can go the opposite direction, but they are absolutely parallel vectors because one of them is a multiple of the other, in this case, -1. So there's one pair, and then all I need is a second pair, and then I've got it. And we have it. So here's AD, 2, 3, -7. Here's BC, 2, 3, -7. That's it. The other 2, you don't worry about. Like I said, those would just be the 2 diagonals. But we found 2 parallel sets of parallel vectors. Therefore, we guarantee we have a parallelogram. There it is. Now, we want to determine if these points are collinear, meaning, do they plot, along the same line like this? Of course, I'm kind of, maybe my dots probably aren't perfect, or do they do something like that, which would not be collinear. Collinear, straight line. There's a couple ways you can go about doing this. Let's see what method I chose here. All right, looks like I went with the length way to do it. The other way would just be creating the vector. Oh, yeah, you can look at it and see if 2 of the vectors add up to be the third vector. That means they would be in a straight line. But I went with the distance formula approach, meaning if they're in a straight line, that guarantees 3 points in a straight line. That guarantees that the length between the farthest 2 points would have to be the exact sum of the inner lengths. Put those dots back up there. So I'll just dot them like this. I don't necessarily worry about the letters, but if the distance between the farthest 2 dots is the exact sum of the other 2 dots, then that guarantees it's in a straight line. Because if not, what would happen is if it's off, like up here, that means the sum of the 2 smaller vectors would be greater than the sum of the one between the farthest 2 points. In other words, you have a triangle instead of a straight line. But the distances, this will prove it's a straight line. So all I did was calculate those distances. That was probably easier than. Now, it doesn't really matter what I called A, B, and C. That really makes no difference because you're not really worrying about, it's not, the lettering is not important, like A, then B, then C. I just gave them names for calculation purposes. All that matters is the longest of those 3 lengths better be the sum of the other 2 lengths. So I came up with vector AB, BC, and AC, calculate each of their lengths using the magnitude. Now, in a previous section about vectors, we talked about the scalar, factoring out the scalar. I used the property here where I pulled out a -2, took the absolute value of it, made a 2, and then did the magnitude. Here I could pull out a 3 and then do the magnitude. So that was already, instead of doing the magnitude and then factoring out the 2 and 3, it was easier just to factor it out first. And this one does not have a common factor other than 1. So, well, anyway, that works out well then, because we have one of the length is 2 square root of 14. We have a 3 square root of 14 and a 1 square root of 14. So 3 square root of 14 would equal, since it's the largest of the 3, it would equal 2 square root of 14 plus 1 square root of 14. So that guarantees those points, without even having to look at them on a graph, that guarantees they're in a straight line. And that concludes the video on space coordinates and vectors in space.